Today we'll talk about the modeling the spread of pandemic disease using the state model that we studied in Unit 2. So all the concepts that we studied will be applying and modeling systems like this. So now suppose that we are given a certain set of population. Let's say it represents the population of a country, and then you have part of population or a subset of population that is vulnerable to disease, or in other words, they are healthy. Which who these are the people who didn't pick any sort of disease. Then there is a subset of population that is infected, and then third type of people are those who are being quarantined or immunized or are dead. So these three subset forms the population of a country. Let us assume. And now, so initially, what it represents is that you will be having population which was initially healthy, which was not affected by any sort of disease, and all the population, or all set of the set of population would be uh, coming in the subset X1. But as soon as the population, a part of population is affected by the disease and catches infection, then a subset is being formed, X2, which represents the people who are being infected. So, and now if we assume that U1 is the rate at which new susceptibles are added to the population. So, which means that these are the subset which are being coming from outside the country and are being added to the population which is vulnerable to disease. So these are the healthy peoples. While then you have a subset which is coming from outside the country, outside the population, which are infected, and they will form the part of the subset X2. So this is again another set which comes from outside the population and is infected. So this system can be represented in the form of state models, and in fact this is not only applicable to pandemic disease, since you can see that it's written viral. So any sort of viral disease that spreads within a country or within a population can be represented by this model. Moreover, this representation can be assigned to the viral messages that keeps on floating in the population. So this can be any sort of thing, any sort of information. It may be an information, it may be a message, it may be a disease, it may be your computer infected by virus. So this model represents it. It will be accompanying all sort of the viral spread or the disease that keeps on happening within the population. So now we see that X1, X2, X3 forms the complete population, where U1 and U2, which are nothing but the input which comes from outside the population. And we can write this spread of the pandemic disease, which exhibits a feedback system, and can be described by the differential equation given as, so you have dx1 by dt, which is what? It's nothing but the rate of change or the state change, and x1 was the subset of population which is vulnerable to disease. So you have healthy people who are vulnerable to disease, who are not immunized or who are not quarantined, and their state change can be represented by a expression minus alpha x1 minus beta x2 plus u1. So this rate of change of the population, part of population who are vulnerable to disease, depends upon x1, which is again the same thing, the part of population vulnerable to disease. X2 are the infected peoples, and then you have U1, which are the people that are coming from outside the population and are vulnerable to disease. So the relation can be understood. So alpha and beta are some coefficient that will be we'll talk about these coefficients and their relations after we form the model, and that again requires some sort of understanding of the time domain analysis of systems. So We'll come through alpha, beta, and gamma terms when we study Unit 3, and we'll try to model this system mathematically and try to draw the graphs using MATLAB, and we'll see that how can the spread be minimized or can be brought to an equilibrium or rest, or what are the conditions which can cause the epidemic or the pandemic to go large. So the minus sign indicates that any increase in the variables like x2 and x1 will cause the rate to drop. Likewise, a positive sign with u1 indicates that as u1 increases, the rate of the state change x1 will increase. So this can also be understood. So we'll try to understand this by the upcoming figures, the signal flow graph, in the next slide. And likewise, you have a relation for state change corresponding to people who are infected. So the rate of change, or the rate at which the people are fetching infection, is equal to uh, beta times x1 minus gamma times x2 plus u2. So the rate of infection people are fetching depends upon the people who are coming from outside and are infected. So this is of course true that your subset is going to increase when you are going to bring population or a part of subset from outside main population, and likewise it's going to drop if you are going to have the part of people who are infected increased. So this part, the subset, if it keeps on increasing, then the rate of change of the infected people will drop. Likewise, if you have vulnerable people there, if the amount of vulnerable people increases, the number of vulnerable people who are vulnerable to disease increases, then in that case again you are going to have the rate of increase in the or the spread of the pandemic disease, that will be increased. Then again you have another variable, that is x3, which represents the subset of the people who are either quarantined or who are immunized or dead. So that will be proportional to the quantities x1 and x2. While in fact x1 and x2 will not depend on x3, because what you did to x3 is you have quarantined them or you have immunized them, or either they are dead. So if such peoples are in the vicinity of x1 and x2, so they are not going to affect x1 and x2. While x1 and x2 will be dependent on each other. So from this relation, while x3 will be dependent on x1 and x2 both. So this will be understood from the SFG in the upcoming slide. Now for a closed population. So for a closed population means that no one from outside being allowed. Then in that case, u1 and u2 will be equal to 0. So this part will become 0 if the population is being closed. So we, from this model, obtain the state representation of the spread of pandemic disease given as follows. So you have the state change x1, x2, x3 dot, which is given by a matrix obtained in terms of alpha, beta, and gamma. So this is nothing but the matrix A. Then you have a state, then plus the matrix B. So this represents the matrix B, and you have two inputs, U1 and U2. This can also be represented by a signal flow graph where you have U1 and U2 as the input given to the system, and this is nothing but x1 dot, or d by dt of x1, and this is x2 dot. So this node represents x2 dot, the state change x2. Now using these equations you can, or the previous equation, because forming state model using or SFG using these equations is easy, and thus you can represent using the previous equations. You can draw the SFG, and we see that there is a dependency of the rate of change of x1 on input u1 on x1 with a minus alpha, and on x2 with a minus beta. Likewise, you have rate of change of the people who are infected depend upon u2, who are the people infected people brought from outside. Then it is proportional to x1, and then again to the amount of people who are infected presently, x2. And then you have the relation x3. So this is x3 dot. So the amount or the rate of change or rate of this way it represents the rate at which the people are being quarantined or being immunized or dead. That depends upon the amount of people who are uh, vulnerable to disease or who are uh, infected. So x1, x2, and x3 forms the part of population. And what does this mean? That x1 you're going to have people who are quarantined from x1. This means that these are the people who are either being immunized or quarantined or are having some sort of natural death because of some other disease other than pandemic like dengue or malaria or any other sort of disease which can cause death to such people. So that type of things are going to form a path with between x1 and x3 dot. So if you're going to immunize the people who are vulnerable to disease, or if you are going to quarantine them, then in that case the rate of immunization and the rate of quarantine will increase with x1. So there is a relation or there is a dependency of the rate of people who are being immunized, quarantined, or being or dying, and that depends upon x1. So if you have a path, you talk about people who are being dying, so that will be because of the disease other than pandemic or uh, this type of death is natural death or other diseases. Then you have a relation between x2 and x3 dot. So this is these amounts to the people who are infected and are being quarantined or are dead. So the rate of the change of x3 or the rate of the people who are being forming the part of subset x3 also depends upon the number of infected peoples, and the relation that we obtain is given here. So they both have positive sign, which means that if x1 is large and x2 is large, it means that x3 is also going to be large. And this represents the state model which can easily be obtained from the SFG in the previous example. And in fact this model will be implemented in either in the form of block. So if you are going to use MATLAB, you can represent this or you can implement this block in the Simulink, which is the part of MATLAB, or you can directly implement these relations like the state space representation or the state variable representation on MATLAB and can analyze the system how it behaves. Now if you talk about the equilibrium point. So equilibrium point is the point at which the system settles in equilibrium or rest condition. That means that during equilibrium you will be having no change in the states, or there will be no increase in the people who are vulnerable to disease, or the people who, or any change will not be observed in the people who are infected. So that is why you will be having dx by dt equal to 0. And if analyze this using the previous relations that we obtained, so you see this relation, you assume that these things are 0, and you assume u1 and u2 is also 0. So in this case, if you consider that no rate of change is being observed in x1, then this implies that x1 and x2 both will be 0. So this is the point of equilibrium. This is the point where things are going to 0. So you'll be having the spread that is being dropped continuously, and you will reach a point of equilibrium where x1 and x2 become 0. So further you will not observe any sort of spread or any sort of uh, increase in the rate of the states. So from this condition, all the conditions the conditions can be obtained from for elimination of pandemic disease from the population. So there are a few more concepts that will be studied in unit 3, and after studying that we'll try to come back to this problem to analyze it, that how this disease spreads using some mathematical relations, and try to implement it on MATLAB, and how is it going to what are the conditions that will cause the spread to come to an equilibrium or halt.